This program is being presented to you by the Heraeus International Winter School on Gravity and Light.
Okay, so let's continue. So welcome to the second central lecture. This is lecture 2, Manifolds. We talked about topological spaces, and it's a fact of life that topological spaces there are so many that mathematicians cannot even classify them. That may be a statement that's a function of time, but in fact there are many topological notions: a Hausdorff space, a connected space, a para-compact space or a compact space, and so on. And if you take all the notions ever invented that are topological notions, that are properties of a topological space that are defined in terms of the topology, and you make a big chart and you say this set has the notion, has not the notion, has the notion, has not the notion. Even notions that are not Boolean valued, yes or no, it has the notion or not. There are notions that are group valued and so on. So that is this group, that is that group. You take this whole, all the notions, and then you ask, are there any two topological sets that are not homeomorphic, so between which there exists not an invertible in both directions continuous map, which maps the topology one-to-one to the other topology, such that all the notions, okay, now it got confusing. So the question is, can you decide on just ticking the notions or not, whether the two spaces are homeomorphic or not? And the answer is there is no such set known of topological notions that you could do that. So for any set you come up with, there are counterexamples. So they're not classified. Well, okay, that's a mathematical problem. A physical problem is really that many sets that you give a topology, they resemble what we think of space-time so little that they're not deemed at the moment. They're not deemed to be useful as models for space-time. But there is a very special type of topological spaces. So I write for space-time physics, classical space-time physics, we may focus, again, a statement that may be a function of time, we may focus on topological spaces. Remember, that's a pair of a set and a chosen topology that can be charted, very, or analogously to how the surface of the Earth is charted. And if you buy many charts that cover the surface of the Earth in an atlas, and an atlas and a chart you can buy in a shop. But you don't need to, because we can construct them. So this special type of topological spaces, these are called topological manifolds. So we start with the definition. A topological space, MO. So you got my philosophy here. I do a little bit of imprecise blah, blah, blah in order to give you an idea, but then comes the precision afterwards. Okay? And of course, you in the future only refer to the precision. Okay. So a topological space MO is called a d-dimensional topological manifold, and I already used my favorite shortcuts here, topological manifold, if. So there's a condition. So a topological manifold is a topological space with an extra condition. It's this charting condition. It says that for every point in the set, there exists an open set U, open with respect to the topology O, of course, containing the point. You can say it's an open set around the point. This is an open set containing the point, such that there exists a map X from this region open set in the manifold into RD, and this D that features here is the D that features here to RD, such that, now comes the actual condition, first of all, such that X is invert, okay, you see already, so it goes to RD, that's correct, but of course it doesn't need to be surjective. One could always make it surjective, but let's say it's not, it goes to the image of the domain under the chart X, and that is supposed to lie in RD, okay, such that X is invertible. That means there is a map X inverse that goes from the image back to U. Okay, it's the first condition. The second condition is that X is continuous. Now you say, aha, continuous. You need to tell me what the topology is on this set. That's not a problem because this is a subset of the entire manifold, of the entire topological space, and this is an open subset. It's not a problem to establish a topology here. And here, this is a subset of RD. So on this M, we of course have the topology O, and on this RD, we choose, because nothing else is said, we choose the standard topology. And with respect to those, we require X is continuous, and then the third condition is that the inverse of X is also continuous. And of course, you learned from the example in the last lecture that if a map is continuous in one-to-one, it still doesn't mean, invertible, it still doesn't mean that the inverse is also continuous. But nevertheless, here we require it. That's it. It's a very simple definition. Yes, pardon me?
It's a manifold if it's continuous with respect to
No.
some topology or with respect
No.
to the standard topology only?
So I take a set with a given topology, whatever it is. And this topological space is called a topological manifold of dimension D if. Now it gets complicated. For every point of this set, there exists an open set in this topology, whatever it is. Doesn't need to be the standard topology, and it can't be, because if M is not RD, I don't even know how to define the standard topology. So some topology, there exists an open set containing the point, but there exists not only such an open set, but there also exists together with this set, for every point, there exists an entire map. It's a lot of data whose existence I require here. There exists a map that takes every point of this set around the point to a subset of RD in an invertible one-to-one manner, which in both directions is continuous. I will clarify this, of course, but this is the definition. And now we'll fill this definition and the elements of this definition with some life. Okay, first thing we note, if X is invertible, then the inverse of course goes in that direction, but then the pre-images of open sets are open, but then the pre-image of U under X inverse is of course X of U, because this was open, this must be open. So because this is open and all of these conditions apply, we know that the image in RD is open. What I will do now, I will first give you 3 examples that I simply draw, and will slowly pick up on the elements of this and give them names that are very familiar to you from navigating maps on the surface of the Earth if you're the captain of a ship. okay? But I don't want to confound you by, well, anyway, so we do it like this. So examples. So the first example, I just draw it and we talk about it, and later on you will be able to actually calculate this. So I take the surface of a donut. But I just really mean the surface of this guy, so the surface of a car tire, okay? And I claim that this surface, this set M donut surface, this is the set M, yeah? And I equip this with some topology. It may inherit from the surrounding R3, because I can put this tire into an R3. I can define it as a subset of R3. I can equip R3 with the standard topology, and I inherit to M the subset topology. But this is not the standard topology. This is the subset topology that originally comes from the standard topology. For instance, or you prescribe one all by yourself. But let's take this one. Then the claim is this is a two-dimensional topological manifold. I don't discuss this technically, but let's nevertheless go through this definition. In order to be that, it must be true that for any point in the set, so I close my eyes and I blindly mark a point in the set, it's on the surface, for any point in the set, there exists an open subset. Well, we know how the open subsets in the induced topology look like, because they will look like this, because I could take an open set in the R3 that looks like this without the boundary. I insect this with the car tire, and what remains is this guy without the boundary. Clear? Because it's this U intersected S. So this is, okay, so I mean it's a quick discussion, but it's all true, I'm saying, okay? So for any point P and M, there exists a U that contains the point, okay, yeah, I found one, satisfied, and there exists a map, there exists one, I need to find some, that takes every point in the set, so this is the U, that takes every point in the set, so for instance, this one, to some part of R2. Aha, so I take some R2 and I take this point to say that one by this map X, right? This is map X. But of course I take this point here also to a point here. And if I take all the points in U to all the points here, I get some open region in R2. Why do I know it's open? Well, because of the invertibility and the continuity in both directions. I get this. And this is true. And so for this arbitrary point, I got this, and it's clear this works everywhere. So I need a one-to-one map, and it needs to be continuous. And one can calculate this and really prove there exist such maps for this example. So this is very nice, because this is precisely what you would do if this was not the torus, if this was the surface of the Earth. You would take the Earth and you would make charts. And in fact, we have, we'll introduce soon the terminology that, okay, let me, before we introduce terminology, let me talk about physics. This thing here, let's consider that to be the real world. Let's say the globe is not a sphere, it's a torus, could be. And this point here, the little cross, is the foot of the Eiffel Tower. I really mean the foot of the Eiffel Tower, the physically existing foot of the Eiffel Tower. That's a point in the real world. You can go there and touch it. It's the foot of the Eiffel Tower. Now, what I do here, I construct a map, and I have posited the existence of a map that maps this situation and the foot of the Eiffel Tower into an element of R2. But R2 is R cross R, is simply a set of pairs of real numbers. Of course, I could have chosen a totally different map into R2, where the foot, here the foot of the Eiffel Tower, because this is R2, we like to say it has components 1, 2, but Anyway, you could have chosen a totally different map of this, and then the image of the foot of the Eiffel Tower, this is x of p. If p is this point, the foot of the Eiffel Tower, x of p has two parts. It has x1 of p and x2 of p, which in this case turn out to be 1 and 2. By choosing such a map, you can say, oh, the Eiffel Tower is at point 1, 2. But it means nothing. Well, it means something because you chose a specific map. So you go to a shop and you buy an atlas and you go to page 27. And this here, this R2, a part of R2, is page 27 of the atlas. And then you start, and then you look and you say, oh, there's the Eiffel Tower, and here's Munich, and so on. Okay? And you say, oh my God, the Eiffel Tower is at 1, 2. That must mean something. Well, of course, it means nothing. It's just 1 centimeter from the lower edge of the chart to here, because the publisher decided to choose the chart like this. If the publisher had decided to choose the chart like this, or to distort the chart, so the publisher has rubber paper and distorts the chart and so on, things look different. Physical meaning, nil, nothing. But the foot of the Eiffel Tower is in the real world, and we like to represent the real world by coordinates in a chart. And in fact, well, I introduced the terminology at this point, so terminology piece 1. A pair ux, and remember, x is not the coordinates or something, x is a map, taking all these points into RD, is called a chart. So a chart consists of the domain of the chart in the real world. U could be the area of Paris. I mean the area of Paris in the real world, that is. The area of Paris that you can go and touch. X of U is the image of the area of Paris in the chart. So this here, no, it is the one I already shaded here. This whole image here, this is Paris, how it appears on paper. You can also touch it, but you touch the paper of the atlas, right? Real world, paper of the atlas. The connection is what the publisher decided to choose as the connection between the two. It's a choice. The publisher also decides whether he takes all of Paris with or without the banlieue and so on. Okay? This is a chart, and all you require is that for every point of the manifold, there exists a chart that contains the point. Around every point of the whole manifold is covered by charts. That is what this definition says. So if you go to a shop and you buy a chart, and your hometown is not on it, you return the atlas to the shop and you say, I feel cheated. There are many charts in there, but not the one I like. You can make sure if for every point there exists such a pair ux with these properties that your little hometown is on there. Okay, so anyway, I already introduced terminology in the context of this example, although I didn't want to, but it doesn't matter. Second example. I take a wire and it's not disconnected here, it's just behind, it's an 8, a figure 8, distorted wire like this. You can also imagine this lying in some R3. You can again take the standard topology on R3, inherit it to here, and then have here the topology on the standard topology here, restricted to the set M. So by this wire, the points of this wire are the points M. The claim is this is a one-dimensional topological manifold. How do the charts look like? Well, for every point there exists an open set U in the real world. For every point in the real world, on the manifold level, there exists such a domain around it, such that every point of the domain is mapped one-to-one to some part of R. Could also be disconnected or not, but roughly like this. So the charts are just one-dimensional. Well, because it's a one-dimensional world. Okay? It's one dimension less. This is more intuitive to us, although it's one dimension higher, but nevertheless, this is that. Third example. You have something like this, and then it bifurcates. It's also a set M. It's clearly a subset, for instance, of R2, right? Can consider it like this. You can certainly, on R2, consider the standard topology on R2, and you can inherit the standard topology to this subset, because M is a subset of this space. So it clearly carries a topology. So for instance, M equipped with the standard topology on the surrounding space, on the superspace, restricted to M. You can do this, and this is a topological space, all right? Topological space, but it fails to be a topological manifold. But fails to be topological manifold. Well, let's investigate this in detail. Investigate the problem. Well, I reproduce this. At this point, there's not a problem. I need to check whether for every point, say this one, there exists an open set around it in the induced topology, like this one, because you see in the R3, this would, for instance, be open. The intersection is this, and so on. Okay, exists an open set, and certainly you can make a map of this bit. Of course, also for this point, there's not a problem. Also for this point, there is not a problem. But this guy here, this makes the problem, because for this guy here, it is not possible to find a neighborhood, an open neighborhood, which, for instance, we can find an open neighborhood, for instance, by taking an open set in R2, and then the subset topology would say that, for instance, this blue set here is open in the subset topology. Very clear. So there's not a problem to find around this point. There is not the problem to find an open set. What you will not be able to do is to find from this blue open set an invertible, in both directions, continuous map into either R1 or R2, because here it bifurcates. Well, I need to work a little I mean, intuitively one sees it. How would you chart this, right? In fact, you can't. In fact, you can't. So this is not a, well, question mark dimensional topological manifold. Okay? So it's very easy to come up with stuff that is not a topological manifold. Or maybe string theorists, they like to think of D-branes and little strings attached to them and stuff. This total configuration is not a topological manifold. You could also say here it is one-dimensional and here it's two-dimensional, but the definition requires there is one D that applies everywhere. And you might say, oh, couldn't we loosen this and have a more interesting notion? Well, it still wouldn't solve the problem what to do about this point where they start touching. You get a similar problem like in the bifurcation.
Just this openness, does this now really embed on this level that it's like an analogous to an open interval? Or?
Because for simplicity, I needed to not only give you a set, I needed to give you a topology on the set in order to have a topological space, in order to then be able to decide whether it's a special topological space, namely topological manifold. I had to provide you with some topology because it serves our intuition for these quick drawn arguments without calculating best if I use the standard topology, which you know intuitively, and pull them back because I know I have to do these intersections. I use this specific standard topology on the surrounding space because I need to say anyway what the topology is. And then it's right if you then have a line and then you ask what are open sets around this. You could take any open set. So say you take a line, a subset in R2 equipped with the standard topology. I can take any open set in R2. For example, all these points in the shaded area together are one open set. Because for every point in this open set, I find a little soft ball that lies entirely in it and so on. This is an open set. And this open set intersected with the subset, intersected with the subset gives these two open intervals, but they're not intervals because this is not the real line, this is already the subset, gives what looks like two open intervals. So in that sense, yes, if you come from the standard topology, it looks like, oh, we already knew this was open or not, but the real argument is via the subset topology, which again I only used in order to quickly draw pictures using your intuition about open sets in R2. Okay, good.
One more question
yes.
about the example 2. When we have a two-dimensional topological manifold.
Here.
Yeah.
Well, two-dimensional one looks like this, for instance.
No, but in the second example, we also live in the R3.
Yes.
Yeah. And then you say, okay, this is a one-dimensional topological manifold.
Yes.
But why is it a one-dimensional? Could I have a two-dimensional manifold?
There is,
do it with the donuts?
there is no continuous map from this U, from this set U, into R2. You cannot do that. You can construct, I think you can construct a bijective map into R2. That's already difficult because you have to wind the interval like this. I'm not entirely sure. I think that's somehow possible, but certainly not a continuous one. That's the point. Okay, so that's, I mean, yes, yeah, that's the point. So it would fail the seer if you increase the D to 2. Okay. I'm not claiming, I mean, this is very intuitive and I want to give you an impression and you need to trust me that it's all true, which I do hand-wavingly, but it's good to first have this impression, but we'll go to specific examples and calculate this also in the tutorials today. Okay. But first to have an impression of the notions is important. Okay. So now comes a lot of terminology, but very good terminology. Terminology. We already had the chart, so I'm always referring to the objects in the definition. And so a Ux, where U and X have the properties from the definition, are a chart of the topological manifold MO. Okay? And the definition requires that around every point there is such a chart, and as I said, that is what a publisher needs to make sure if he sells you an atlas that satisfies you, a set A that contains a collection of charts. So let's call them U alpha, X alpha. So alpha is now a label. You have many, many sets U, many, many sets X. This label can come from any arbitrary index set. So you have a huge, possibly a huge amount of charts. Such a collection is called an atlas. Well, it's very intuitive. A collection of charts is an atlas if there's only one condition, that if you take the union of all the chart domains. Remember, this chart domain is Paris, the real area of Paris in the real world. X of U can then reconstruct the images of Paris. But if all the areas that are covered by the chart, if you take them all together, they may have huge overlap, but if you take them all together, you should recover the entire real world. So every piece of the real world should be covered, and then you call a collection of charts an atlas of the world. It's a very important notion. So this is an atlas of the topological manifold, if this is true. Very intuitive. Okay. That was that. Now, a further piece is called this X that goes from U, from the piece of the real world into the image of the piece of the real world, which happens to lie in a d-dimensional chart. Well, if unfortunately space-time is four-dimensional, you cannot print an atlas of space-time by printing on sheets of paper. You need to print on four-dimensional sheets of paper, which mathematically you can do, practically you can't. Okay? The surface of the Earth is it's lucky that it's two-dimensional, right? Okay, so this map is called the chart map, because obviously you can have the same domain in the real world, but you could choose different chart maps, represent them differently in your atlas. But it must be continuous. Okay. And now comes a really important piece. Blackboard, please. Now comes an important piece. Namely, you see, if a map goes from some subset into RD, what does it mean to go to RD? I cannot stop emphasizing RD is just R cross R cross R and so on, is the set of D tuples. They're just D numbers in an order. Okay? How do I provide you with this information? Well, I can provide you how a point in here, how a point P in there is mapped by X to an element in RD. Well, so the result must be an object with D entries. Is that right, clear? So for any point here, X of P, the image, is an object with D entries. Each entry will depend on what point you chose. So you have a number, a real number x1 of P, a real number x2 of P, and so on, and a real number xd of P. So what are the x's? Where xi, the ith x, is a map that takes a point in U, of course, and maps it only to R, so not to RD, but to a real number, namely the x2 of P, to a real number, that's then here the second element, to a real number, and this you have for I equals 1, 2, 3 up to D. In other words, a chart map that associates with each point D real numbers is of course the same information as giving you D many maps called xi. So x1 is a totally different map from x2 that take the points into R. Okay? These are the component maps, if you wish. The component maps. And these component maps, please, yeah, thank you. These component maps, they have a name. Call, so if Ux is a chart, thank you. So if Ux is a chart, then the maps x1 from U to R down to xd of U to R, which is information that's equivalent to the one map x from U to RD, right? These guys are called the coordinate maps. Okay? So this is the next piece of terminology. And of course, what the okay, so that's this. And then we have, if P is a point in the chart domain, in the domain of a chart, then x1 of P is the first coordinate of the point P with respect to the chosen chart. Because if you choose another chart, of course, that will be another number. X of P is the first coordinate. So X of P may be 1. X of 2 of P is the second coordinate of the point P. P is the foot of the Eiffel Tower in the real world. X2 of P is what happens to be the number on your publisher's chart where he puts, in this direction, the foot of the Eiffel Tower in the chart. This is man-made. Charts are a figment of our imagination. We imagine charts. Charts have nothing to do with physics. They may be very useful. An atlas is extremely useful. But nobody would say because a publisher printed an atlas upside down that it would be less comfortable to live in that part of the world. An atlas is something imagined. Most of undergraduate physics we formulate in atlases, and we very much confuse what is imagined and what is real. I will emphasize therefore very often what is the real world and what is an image, an arbitrary image of it. It took Einstein 3 years to clarify this. It takes us 3 days. Okay, so that's excellent. Good. So, but this is a key point. This is a key point. And it's totally obvious, totally obvious. You know this from Lagrangian mechanics. You have a physical system that moves on some configuration space. And you all learned that you can choose generalized coordinates, that you can choose other generalized coordinates. Choosing coordinates is choosing charts. Choosing different charts is choosing different coordinates. Does the bird that flies by here care about my idea about charts? No. The bird is not impressed. What would be physics? Well, let's not say a bird. A bird has this free will thing. Let's take a stone without free will. You throw a stone. What would physics be if your stone was impressed by your thinking about a chart, one chart or the other? It would be physics with telekinesis. I could start moving things by imagining different charts. Physicists call these frames of reference or whatnot, okay, or generalized coordinates. If that comes up tomorrow, if somebody conducts an experiment and we're sure, okay, the experiment proves by thinking I can move things, not a problem, we do chart-dependent physics. But since that is not the case, all we do, until further notice, is we do chart-independent physics. We'll very much think about the real world. The foot of the Eiffel Tower is a real point that is there, has nothing to do with changing coordinates. Changing coordinates doesn't move the foot of the Eiffel Tower. Okay? We do physics without telekinesis. That's the programmatic aim. Okay, good. So these are the coordinates of a point and the coordinate maps. Okay, so I already explained the foot of the Eiffel Tower. I don't need to do this again. I will look at quarter past. We have until a quarter past, is that right? Until when do we, pardon me? 12. Until 12. Okay, perfect. Okay, let's make another example. So now take as the real world the surface, the points in R2. I should already say surface, the points in R2. It's all these pairs. And now we look at the chart U, just an example, that is all these points, but I can remove the element 0, 0. By the way, if I say M is the set R2, a set, okay, there is a piece of R2, and it consists of the points. What is it if the set, so this is a little aside that's important, a set, what's the difference between the set 1, 2 and the set 2, 1? None, yeah, okay, I already wrote the equal sign. There's no difference. A set has no order. If I consider this as a set, I can rip it apart, I can grind it, I can make a powder of this. Then I fill the powder in a glass, and then I shake the glass, and then I come to you and I pour the little pile of powder there, and I say, there you got your R2. We like to think of R2 as being somehow this thing. R2 is a powder because R2 is a set. Now I can shake it and I change all relations between the points that we may imagine. Now I give it a little more structure if I equip it with the standard topology. Then I can take this like a rubber piece of paper and I can pull it and so on, but I cannot rip it apart because that would be non-continuous. Okay, so the R2 you're thinking of usually at least is the topological space R2 with the standard topology, but as a pure set it's a powder. Okay. Okay, that's just as a warning, what is a set, what's a topological space, a topological manifold, and so on and so on. Okay, so anyway, we take this as a topological space, we take this set, and now I invent a chart, and the chart I invent is the following. X needs to go from U into R2, and it's as follows. R2 elements as a set, as a powder, is nevertheless pairs of numbers as a set, and I map this to, now because I feel like it, to minus m minus n, because that's an element of R2. I can do that. I arbitrarily took the 0, 0 element out. So let me draw a picture of this. So if you say this is the real world, it's the real blackboard, right? The real blackboard is this, if it extends. It's the blackboard I can touch. It's the real world. But now I take the real blackboard and I only consider the real blackboard without a point, which maybe the 0, 0. And I map this to a chart. Now this is the chart you have in your book. It's a picture of the blackboard, for instance, right? And you map this and you see, you take this point to this point, and you take that point to this point, and so on. And if you have here, for instance, a point set that looks like this, then you know that the map I just produced takes it to here. So this would be what your publisher, if you have an atlas that is an atlas of the blackboard, I took this point out for fun, and you want to represent this real life situation, namely the chalk dust that's here on the blackboard. You want to draw it into your map. You take your chart map X, and every single point you take by the chart map X to every single point here, and this is the image of your real world. It's a perfect chart map. You might say, oh, it inverts the real world. What do you mean? It's a chart map. It's as good as any other chart map. Okay? Yes?
But if you give the blackboard already numbers of R2, you assume already that's not the real world. You have already mapped the blackboard to...
Yes. Yes. In order to, you're absolutely right, it's a notorious problem of emphasizing this, because the real world doesn't consist of points. The point is, what I would have to do is what I did in the beginning. I indicated a map by really saying this element, and this is on the blackboard. I point with my finger at it. I take this one, I assign this the number -1, -2. Okay? If I do this, so it's more like these arrows I drew before. And what you need to do in real life, you need to go and you need to put little flags. And you say, here, in the real world, there's a flag. It's here on the moon, and it's our flag, and we call this point 1, 2. That is putting up flags that have numbers on them is inventing a chart. And that's what, of course, what gold diggers do. They put their claim and they draw lines, and, you know, stuff like this. So it's absolutely true. And in fact, I will draw a diagram in a second. In physics, we always ignore the real world. We only talk about charts and chart representatives of the real world. But at least mathematically, we should put it in order to know what we're talking about. Okay, so we can do it like this, but we can do another chart map on the same domain. We can do the following. I can do the points Mn, if you're happy with that. We already put up flags here, okay? And I can map it to square root of m squared plus n squared arctangent n over m. If you think that's crazy, then you say polar coordinates are crazy, because now again I have the real world, and say in the real world, on this blackboard, the dust chalk that lies on this circle, if I map the situation into a chart on paper, then now the first coordinate, in quotation mark, is the distance from the origin, intuitively speaking. Well, it's just this algebraic expression. And the second one is an angle it takes with, say, this axis, roughly speaking. So the chart domain of the entire R2, without the 0, 0 element, the entire chart domain is this set here. It runs here only from 0 to 2 pi. Oh, I need to take out, I'm sorry, I take out the entire, take the slit plane here. So I take out the entire x-axis, so without A0, where A is in R. So I do not only take out the point, I could have also done this here, I take out this entire slit for certain reasons. Don't worry about it. So this, pardon me? I don't understand. A is in R? Ah, yeah. Thank you. Thank you. And R plus 0. Now we got it. Okay, so so the chart domain is this infinite, half-infinite strip, because it ends here. That's the point. I took the 0 out. Without
You're only taking out what is positive.
0. R plus. Yeah, sorry. The negative ones are still in here, but I took out the 0 as well. This is everything behind it. I took it out, including the 0. I take the M0, I took it out. M equals 0 is taken out. Okay, so this is the X or the Y, let's call this the map Y. This is the map Y of U, of this real world. And now please draw the circle in the map. How does it look like? Yes, exactly. The part of the circle that is covered by this domain, well, this point of course cannot belong to it because it's not in U, is this. So we have a perfect chart, and this is the image of the real life circle. In this chart it looks like this. Well, this is what you call generalized coordinates in classical mechanics. You would probably say, oh, this is the r coordinate and this is the phi coordinate, but we call them the x1 of p and the x2 of p. Could call them the phi of p and r of p, but this is just what it is. Okay, so again, the same real world situation. Of course, here, if you had the circle, it would appear as the circle. You just don't see that it's inverted, like the F, right? That's it. Okay, so any chart you can come up with is covered by this definition, and in the chart things may look very different from the real world. You need to know how the charts are related to the real world. Okay. Third section, chart transition maps. So these are objects that are they are derived objects. Objects derived from certain charts we already have. So they're actually not worth mentioning, but they're heavily used by physicists. Hence, we introduced them. Imagine a situation, or imagine two charts, Ux and Vy, so different domains and different prescriptions of how to map into a chart. Imagine two charts with overlapping regions. So in the real world, let's say this is now the real world, there is one chart domain U and another chart domain V, and they have a non-empty overlap. That is what I mean, they're overlapping. Their overlap is non-empty. Now, U comes with a chart map that takes any point in U to some piece of R2 or RD. Well, in particular, it takes a point in the intersection there. So I can take a point in the intersection by the chart map X that comes with the U into a point in some chart. Why? Well, because the intersection certainly is a part of U. Now, because that point lies in the intersection, I may use alternatively the chart map that comes with the V region, because it obviously also lies in the V region, and I can alternatively map the very same point in the real world, the foot of the Eiffel Tower. The same point in the real world, I can map it into another chart. Of course, you will turn the pages of your chart and your Eiffel Tower will usually appear more than once. Will appear on that chart here and on the other chart here, because the charts always have a little overlap in order for you to navigate. Well, it will turn out that we also need this overlap to navigate. Okay, so that means you can think about after you say, okay, this x is defined on all of u, but you can certainly restrict it to only u intersected v, and the y map can also be restricted to u intersected v. Now, if you map the whole x of u, it would maybe look like this. This would be x of u. But if you map only the intersection, that will be only that part. The same here, if you map the whole v by y, it may be y of v. But if you only map the intersection, it will only be maybe this part. So this is x of u intersected v, and this guy here is y of u intersected v. I think the idea is pretty clear. Now, you have on the chart on page 7, you have the foot of the Eiffel Tower here. In the chart on page 28, you have the foot of the Eiffel Tower here. And one obvious question is, what if you have to turn pages? How can you directly take the coordinates on page 7 and translate them in the coordinates on page 28? That would be very useful, because here you use this putting up flags on the surface of the Earth in order to make this map. This was exactly Gerhard's concern. You already chose somehow coordinates. Well, just to quickly write this down, but you need to put maps. Wouldn't it be great if I could just take these coordinates and had a rule how to translate them to those? Well, it's very simple. This map x is invertible. So I can take the yellow point here and I can feed it into the inverse of x. X inverse takes me to the real foot of the Eiffel Tower. This is the foot of the Eiffel Tower in the real world. And then I apply the y map to it. And then I have the coordinates in the other chart. Well, but this is nothing but y after x inverse applied to the representative of the foot of the Eiffel Tower in this chart. So this is the picture, and you see this requires artists' skills. It's cleverer to do this formally. U intersected v, ux and y, vy are charts. You can map this by x to the image of x u intersected v, which is, and that's now a point I wish to emphasize, of course, is an element of RD, subset of RD. You can take the entire subset, so this is the entire subset you take, by y, you go to y of u intersected v, subset of the same, not the same, well, of RD, forget the same thing. And now I can construct a map from this set to that set, namely from the shaded set to the shaded set, and that map is y after x inverse. And this map, y after x inverse, this guy here, this is called the chart transition map. And if physicists talk about a change of coordinates or a change of chart, you know, the coordinates are just the component maps. The coordinate maps are just the component maps of the chart map. If physicists talk about a change of coordinates, they go to one of their favorite imaginations and transform to another of their favorite imaginations. Imaginations, nevertheless. The real world sits up here. And because the chart maps are invertible and in both directions continuous, the chart transition map is a map from undergraduate analysis, a part of RD to another part of RD, from an open part of RD at that to another open part of RD. And this will be continuous because these guys are continuous in both directions, and the composition of continuous maps, so remember the end of last lecture, is continuous. Now, as physicists changing coordinates, we start in one coordinate system and we say, let's start in the Cartesian coordinate system. That's a good one. Well, it's just fantasy. Okay, but you start there and then you say, oh, but now this problem is better to go to the polar coordinate system and so on. You're just moving back and forth here and there. And what you never touch as a mathematical object is the real world. You never use the foot of the Eiffel Tower. You only take your coordinates of the foot of the Eiffel Tower. Now, this is fair enough, and of course it's correct in what you predict in Lagrangian mechanics, everything is fine, but it can lead you to the philosophical problem of somehow imagining that there is some reality to the coordinates of the foot of the Eiffel Tower. And even if you understood you can choose other coordinates, you might hold the position that, well, the Cartesian coordinates, those are the real coordinates, and hence we don't call them generalized coordinates. And the other coordinates, they're kind of not so real as the other. This means nothing, okay? So these are all just notions you invent because the theory is usually presented within this yellow box. One of the advantages of looking at this manifold picture is you can calculate very nicely here, but please do not forget that there's the real world you want to talk about. And the foot of the Eiffel Tower is the point P in here, and it doesn't care about whether you look at this chart map or that chart map. And this is something that took Einstein 3 years to fully understand. He understood it half, or 3/4, or 99%, and that's wrong. Okay? You need to understand it 100%, and this manifold picture gives you this 100%. That's the chart transition map. Aha! Now, the chart transition maps, they contain this fantastic information. So you have a chart, say you have an atlas that has many pages. And on these pages, there is, say, some continent that looks like this and some that looks like this. Now, on another chart, there is a continent like this and there's something like this and so on. And of course you realize, oh, this one is actually the same part as this one. In the chart transition maps here, these guys will actually say, oh, here, I don't know what this is, oh dear, Madrid. Madrid is again to be found here, so there needs to be a chart transition map from here to here, that's this. The chart transition map contains the information, so this is informally, but it's a good way to think about it, contains the instructions, is better, contains the instructions how to glue together the charts of an atlas. Imagine you're the captain of a ship. And these modern ships, you can sit deep down in the ship, you have no windows, no nothing, and it's a long cruise, and you have nothing to do. You have an atlas of the world with you, and you're very desperate, and it's a single-sided printed atlas, okay? Single page, one side on one page. And you're very frustrated, no women there, whatever, and you pull out the charts because you're so frustrated. And then you have some glue. And you decide to glue together the charts in their overlap regions, which you can clearly identify, like in the street atlas. What do you get if you glue them all together? You get a paper model of the sphere. You get a sphere if you glue them all together, topologically speaking. Well, if the charts are small enough, it looks a little bit wiggly, but you essentially get a sphere. And all you used is the information, this part looks like this part, green continent, glued together here like this, you get the sphere. And what you did is just, you identified this point in this chart with the corresponding point there and glued them together. It's a gluing instruction, which point with which point. You may have to bend the paper a little and so on, and then you get a sphere. In the tutorial today, you'll have also charts of a world, and you need to glue them together. And they look like now normal charts, but you will be surprised what you get out when you glue them together. It's the chart transition maps that you can have all the information about the real world globally, topologically, in the chart transition maps. Hence, they're so beloved by physicists. It's very good information with a data structure, RD to RD, which is very simple to implement mathematically. But the meaning of it is only what you glue together. Nobody would say if you have an atlas, you understood that the world is a sphere, the surface of the earth is a sphere, unless you start gluing together. Okay? Okay, so those are the chart transition maps. Now we come to a very important point. I call it a blackboard, please. So the headline is Manifold Philosophy. What is the whole philosophy of writing down manifolds? Now, the full extent of this we will only understand once we start discussing differentiability of curves and functions. So far we only talk about continuity, no jumps. But differentiability of a curve means there's everywhere a tangent, roughly speaking. Okay? The full extent we'll only understand there. But the basic idea is the following. I have the real world, and I can if I have an atlas, I can represent the real world in charts. For instance, I have the course of a ship in the real world, so the bubbles it leaves in the sea when it moves. These points in the real world. I can represent them by drawing them in a chart. That's what navigators do. They put the course in their charts. And thereby they represent what the ship in the real world did. Now, the navigator puts the course of the ship in a chart. Would the navigator be surprised, or his supervisor at home, if all of a sudden the course of the ship would jump to another point and continue from there? Or he would be very much surprised. He would say, how did you do that? How did you do that? But what is the argument that this supervisor would have to give why this is unusual? Well, he would have to argue that the chart maps from the real world into the chart are bijective and continuous, that in the charts you've chose the standard topology, blub, 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 blub. So he would have to argue from there that a discontinuity of the curve in the chart, which is a curve from the real numbers, the curve parameter, into R2. This is what we teach undergraduate students. A point particle is given by a curve in R3 or in R2. But this is just in the chart. So we shouldn't think of the curve of in R3 as the real curve in the real world. It's the image of the curve in a chart you chose. Right? That's this. But because of the postulated continuity or the constructed continuity, you would indeed be able to judge the continuity of the curve in the real world from the continuity in the chart. Right? So what you can do, instead of defining continuity directly in the real world, which you can because the real world is a topological space and you can define continuity of curves, you could instead, and that's the manifold philosophy, push the objects you want to study, the real world objects, push them down into the charts, look at the chart representatives using the chart maps, study the objects in the charts, which is very simple because these are curves from R to R2, or they're functions from R2 to R, like a temperature distribution drawn in a chart. These are objects you know from undergraduate analysis. You study them there, and then you get the idea, couldn't we define properties of objects in the real world by properties that our chart representatives have? Right? And the answer is yes, you can, but you got to be careful. So that's fourth, manifold philosophy. Often it is desirable, or in brackets, or indeed the only way, and we will see examples for this, or indeed the only way to define properties. And now I give examples in brackets, but of course we will have more examples, like continuity of real-world objects for instance, a curve in the real world, a curve gamma from R to M is a curve in the real world, by judging suitable conditions not on the object itself, not on the real world object, itself, but on a chart representative or image, I make this clear in a second in an example, on a chart representative of that real world object. The advantage of such an approach is obvious, or the advantages. The advantages are that in a chart, let's do this for the example of a curve. Real world, course of the ship in the real world is a curve gamma from some parameter set into M. And now I choose a chart, U, and I look at that portion of the curve that lies in the chart U. So only look at that portion of the curve. That makes the argument simpler, but you can generalize this. And you map this curve into a chart. So this is the image of the U part. This is x of U. And this curve will, in this chart, maybe look like this. And this is x. This is x after gamma. Why? Well, let's draw it here. The U comes with an x chart into x of U, lies in RD. And then you can look, instead of looking at the curve in the real world, you can look at this object here, which is x after gamma. So you first execute gamma and then x. And this is, of course, the curve in the chart, because it goes from a real parameter to a part of R2. This is what you're told in undergraduate physics. This is what you say is the trajectory, for instance, of a particle in R3 or something like this. But you see, in fact, it's only the chart representative of this. The curve in the real world is this object up here. Okay? But now, of course, you're instructed in undergraduate physics to say this is the trajectory of the particle and it must be continuous. So what you really say is, if this chart representative is continuous, which you know by undergraduate analysis what it means, R to RD, continuous. If this is continuous, then you say the particle path, which is in the real world, is continuous. So you do precisely this by tacit assumption. You do this, you say, you judge, you define the property like continuity of a real world object, the real path of the real ship in the real world, by judging suitable conditions. In this case, you also call it continuity, you call it undergraduate continuity, not on the real world object, but on the chart representative of it. It's an advantage because you can use undergraduate analysis in charts. Mathematics in charts is mathematics on the real numbers. It's not so complicated, it's a good thing. But it has a disadvantage. It has a philosophical disadvantage, which I already mentioned. The philosophical disadvantage is you might start confusing what is a chart image, what is the real world object. Assuming you are Einstein and you spend 3 years thinking about it and you no longer fall into that trap, there's yet another disadvantage. The notion you define down here by referring to the chart representation may be ill-defined. What does that mean? What's ill definition? A definition says this and this is defined like so and so. But here we want to assign a property to this object gamma, but we judge it by the object x after gamma, where x is a figment of our imagination. So we imagine something with certain conditions, okay, and we say, well, including my fantasy I afford here, I assign a property to this object which has nothing to do with the fantasy whatsoever. The bird doesn't care about my imagined chart. So how nuts may it be, it can be very nuts, to take the composite object, including my fantasy, my superstition you could call it, and judge the path of the bird and assign the path of the real bird a property that also depends on my thinking. That is very dangerous, unless I ensure that if I have any other thinking, the result doesn't change. So maybe ill-defined, to avoid that, maybe ill-defined because an arbitrarily chosen chart is employed. We need to make sure that property, that the defined property does not change if we afford another fantasy. Well, the fantasy is another chart, because that's just something I'm thinking about. Okay, so formally, it's a very simple idea. I have a curve. Do it for a curve. I could do it for a function on a domain, for anything. Okay, I take a curve and I say, so now fantasies will be in red. Fantasies are red. Well, this is at least a part of the real world, but what is a real fantasy is this chart map, how this part is mapped. This is here, and so we have the composite map that consists of a little bit of fantasy, well, of arbitrary choice, of superstition, together with something in the real world. Now I look at this object and I say, whatever properties this has, say continuity, I then call continuity of this guy here. That may be a problem, unless you ensure that another fantasy, so sorry, fantasies are in color, another fantasy is the yellow fantasy, another chart goes to y of u, and then you have another representative, y after gamma, again an object that uses some fantasy, but if you can ensure that if in some chart some property holds, if you can ensure it holds in any other chart too, for any other fantasy, then it's obviously independent of your choice of fantasy. So you may use fantasy if you ensure that it's independent of fantasy. You know this maybe from equivalence relations. If you define the sum, you define an operation on equivalence classes and you define it by using representatives of each class, but you need to make sure it's independent of the representative chosen, because choice of a representative is a pick you make arbitrarily and so on. Okay, so how can we ensure for, say, continuity? I say, okay, this continuous I can check because it goes from R to a subset of RD, both equipped with the standard topology, undergraduate analysis. Assume I know this is continuous. Can I already conclude that with respect to any other chart, it's also continuous? Yes, I can, because this map here is of course the same one as if I go down here and then by here to here. So in other words, y after gamma, that's this one, can be written as y after x backwards after x after gamma. So this is just looking at this diagram. But because the composition is associative, it's y after x inverse after x after gamma, I can do, you only inserted the identity. Okay, you can think of this like that algebraically, but you can think of it in this way. Whatever way you think about it, you see, of course, I have here this chart transition map, y after x inverse. We know that those are continuous. We argued this before. We know that x after gamma is continuous. That was our starting assumption. But then the composition of continuous maps is continuous. So for the notion of continuity of this curve from R to RD, the continuity of the chart transition map saved the day. The continuity of the chart transition map makes this chart-dependent definition fantasy independent or choice independent. I emphasize fantasy to be polemic, but it makes it independent of the choice of chart. Now imagine something different. Imagine you got the idea that undergraduate physicist lecturers get to define x after gamma, which after all is a map from R into Rd. They say, let's check whether this is a differentiable map, whether we can find the derivative of this map, which at a point you would call the velocity of the curve or something. But we're in a chart. Now, let's say you say if this is differentiable as a map from R to Rd, let's say you want to say, then you define the curve gamma in the real world, you call that differentiable. No? Obviously, you can't decide this immediately because from R into some set with a topology, you don't have enough structure. For instance, you can't do sums and subtractions and divisions, which you need for a differential quotient, right? You need a difference and a division, so addition and multiplication, roughly speaking, in order to, you cannot define differentiability at the manifold level. You could with continuity and you could push it, and all we did before, you could have decided at the manifold level or at the chart level. But now if you go to differentiability, which we will do in the next lecture, you can only talk about the chart representatives because here from R to Rd, you can establish an addition and you can establish a multiplication with scalars in order to do the differential quotient. But now imagine you did this. Could you still say, if I know that this here is differentiable, you can check this is not a problem. You can check whether this is differentiable. But are you guaranteed that this one is then differentiable too? So it's independent of your chart choice? No, you can't, because this chart transition map here, y after x inverse, we're only guaranteed that it is continuous. But if you have a differentiable function and you compose it with a continuous function, it may be that the result is only continuous but not differentiable, because the chart transition map can introduce into a nice smooth curve a little edge that's still continuous to do something like this, but it's no longer differentiable. You have no unique tangent. So you see, oh my God, on a topological manifold with its continuous chart transition maps, we cannot define a notion of differentiability by defining it in the charts. But in the charts is our only possibility. And we would like to have a way to lift this notion in the chart to here, such for any other chart, oh, where do the charts come from? They come from a big atlas. What if we take a huge atlas with lots of topological charts with continuous transition functions, and we rip off page 7, page 113, and page 1080, because those were the ones that had only continuous transition functions from Rd to Rd, but transition functions that were not differentiable. If you take out all the troublemaking charts, then all of a sudden you have a restricted atlas, an artificially restricted atlas. However, if you agree to take charts only from the restricted atlas, where all the transition functions are smooth, you have composition, or differentiable, you have composition of differentiable maps, which are again differentiable, and you got rid of your problem. But now I give you for Christmas a maximal atlas. What's a maximal atlas? An maximal topological atlas is one that contains every chart it could possibly contain. Lots of redundancy. It's a maximal atlas of topological space. Now by having to rip out page number n, n prime, and triple prime, and so on, I give you information because I could encode a message in that, right? Number 7, number 13, and so on is the numbers of in the alphabet. You know, I could send you a message, I love you, or something, okay? Ripping out charts is information. So reducing a maximal atlas by ripping out certain charts that make trouble for the notions we want to define means providing information. And this additional information is called the prescription of a differentiable atlas. And that will be the next lecture. We'll do that, and then we'll make the differentiability work. And that's a major step in understanding space-time. Please.
I'd like to come back to that. I'm one of those happy physicists who don't care about chart that we can conclude for any other chart. I'm still missing the step, how can we prove that the continuity, because we have defined continuity in a precise way
Yes.
in your first lecture, this step
Yes.
is missing.
Yes, that's right. So this I would call R continuity. I called it undergraduate continuity. This one was the continuity we defined. The only thing I showed so far, and it's a very valid and important observation, the only thing I showed so far is that my idea of R continuity gives some notion of R continuity on the gamma. I could call it the lifted R continuity. That it has to do with the continuity we were talking about before hasn't been proven yet by this, but it can be proven very simply, because as much as if I know that if G, so if I have a map, there it is, gamma, R, U, RD, roughly speaking, X, gamma, I know if this is continuous and this is continuous, I can conclude that this is continuous. But what you are asking for is, if you know that this is continuous and that is R continuous, can you prove from these two that this is continuous in the original sense? And the answer is yes, you can. It's a few lines. So indeed, because with differentiability, it's an accident of topology that I can decide it at this level in the first place. Hence, I de-emphasize this point. Whereas differentiability, I have no differentiability at the manifold level to compare with. That's the question you asked. How does it compare to the original notion of continuity? But for other notions, I do not even have something to compare with. And then you're thrown back to the manifold and to the chart picture. And then well-definition is all that remains to be cared of. Thank you. Yes?
You need the assumption that it's invertible and the inverse is continuous as well, right?
In here, I'm not sure. Could be. Let me think about it. It could be that you're right, that you need the continuity of the inverse here as well in order to do the red implication arrow. It could be. I think not, but I'm not sure. It's simple. We do this in the break. Okay. Please, another question? Okay, if there are no further questions, I invite you to the tutorials at 2 o'clock.